All right. So this is 9.6. All of it. So today we're going to be solving right triangles. That's our goal. But in order to do solving these right triangles, there's one thing that we need to find out, which is angle measures. We don't know how to find angle measures. Now, I'm going to fill in this little chart right here, or this triangle. Say this is triangle ABC. And this is going to be 1, square root of 2, and this is going to be 45 degrees. So, our goal in this problem is to determine what the measurement of angle B is without adding or subtracting the other angle measures. So, looking at this function, it's a triangle, come on. We can kind of determine what angle B is going to be already. Given that we have 90 degrees and a 45 degree angle, we know that angle B is going to equal 45. Now, why do I say angle B is going to equal 45 degrees? Well, we can do 180 minus 90 minus 45, and that will get me 45. This is also a special right triangle, the 45, 45, 90 triangle. So our end goal is to find out what the measurement of angle B is, but we're not going to do it with adding or subtracting. So this 45 right here is our goal. This is what we're trying to head towards. So yeah, cool. All right. With this in mind, with 45, we can start thinking of ways that we can try to find this angle measure. Now, going back to previous lessons like 9.4 and 9.5, we can use some ways to set up formulas to find missing information. Those formulas being formed by SOHCAHTOA. Remember that it's sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. So with SOHCAHTOA, we can kind of piece together things about this B in order to find it. So since I'm working with angle B, we can go at it one of two ways. We can pick which sine, cosine, or tangent we want to work with in order to try to find this angle measure. It depends on what kind of, I don't know, it depends on what side lengths you want to work with. In our case, we're going to work with sine. So let's say I want to work with the sine portion of, I don't know, the trig functions. That means I need to work with opposite over hypotenuse. So I need to kind of point out what's opposite and what's the hypotenuse. From angle B, the hypotenuse is the square root of 2, and this opposite is going to be the 1, and adjacent will be this other one. Opposite side length, adjacent side length, hypotenuse. You'll get the same answer if you do this with cosine or tangent. It doesn't matter which way you do it, but we're going to use sine, opposite, and hypotenuse to help us go through this. So let's start setting things up to find the measurement of angle B. So using sine is equal to opposite over hypotenuse, we can start plugging in information. So my sine of B is equal to 1 over the square root of 2. I don't like the square root of 2 in my denominator, so we get rid of it by multiplying the square root on the numerator and denominator. So I end up with the square root of 2 over the square root of 4. Getting rid of that square root of 4, I'd end up with the square root of 2 over 2. So rewriting, I have sine of B is equal to the square root of 2 over 2. And now I'm in a pickle. Speaking of pickles, I'm almost out of my protein bar. I just got back from a run. I'm hungry. And dinner ain't happening until like 6. and it's 4 o'clock. I'm gonna actually die. Anyways, I need to get rid of the sine somehow to get b by itself. Let's try getting rid of it. Now, when it comes to getting rid of sine, our go-to reaction to get rid of sine is to divide it. So let's try dividing it. Now, I'm going to do it on the calculator because I don't want to write it out. There we go. So square root of 2 over 2. I'm putting it in parentheses so that it works with each other. Then I got to divide it by sine. Oh, wait. What am I going to put into sine? Since I'm trying to find this b right here. But if I'm trying to put in sine, I don't know what I'm going to put in it to actually do the division. Let's just try hitting enter. I get an error. So it looks like I can't divide sine. And likewise, I couldn't multiply it either. I couldn't multiply, would give me the same thing, getting an error. So dividing and multiplying don't work. This is when the concept of inverses come into play. Typically when we see an inverse, which is something that we've done a lot, it's like an inverse operation, like multiplication and subtraction. These are inverses. I meant addition and subtraction, not multiplication. Multiplication and division are inverses. A square and a square root are inverses. See, I've been harping on inverses, like especially with like this one, that these are inverses a little bit, because inverses are coming into play today. To find this angle measure, and since we can't get rid of sine by doing like division or multiplication, to get rid of the sine, we are going to have to take the inverse of sine. What do I mean by taking the inverse? Well, since we have the sine of b, instead I can multiply this by the sine of -1. And since I'm multiplying on one side, I gotta keep it consistent and multiply it on the other side. So sine of -1. And then these two signs will cancel out, leaving us just this measurement of b. And that will be equal to the sine inverse of square root of 2 over 2. And when we are working with this on our calculator, see this button right here, the sine? Above it in blue, we have sine -1. Same with above the cosine, cosine -1, and tangent -1. These are the inverse functions. And you hit the second button and then hit sine. It comes up. Notice on the square button, the square root is the inverse of it. Not a lot of the blue, but some of the blues on our calculator are inverses of each other. This ln and e to the x, these are inverses. This is a natural log. This is kind of algebra 2e territory, so next year you'll learn a little bit about this. But a lot of the blues are inverses of each other, so we can keep that in mind when we work. So I'm going to do the inverse of sine, and then I'm going to plug in the square root of 2 over 2. And would you look at that? I get 45. Cool. So that means my measurement of B is equal to 45 degrees. And we found that by doing the inverse of sine. Now, I believe if we did cosine, we'd end up with square root of 2 over 2 still. So we can type that in and we'll check it out. See if we get 45. You get 45. Now, the inverse tangent version of this, given the tangent function, it would be opposite over adjacent. So we'd take the tangent of 1 over 1, which is just 1. So the inverse tangent of 1 over 1 would also give me 45. So no matter which way you do this, you will get the right answer as long as you plug in the right side lengths. But this is our introduction to inverse functions. So let's go to the next page. Crap. Nah, that's okay. I was like, I'm kind of freeballing right now with the notes because I don't have my notebook, but that's okay. I'll figure something out for this. Anyways, for inverse trig ratios, let angle A be an acute angle. So this one right here. We have 3 statements. We have the inverse tangent statement. So if tangent of A is equal to x, then the inverse tangent of x is equal to the measurement of angle A. Inverse sine says that if sine A is equal to x, then the inverse of sine x is equal to the measurement of A. And then inverse cosine, if cosine A is equal to x, then cosine inverse x is equal to the measurement of angle A. Notice how if we go from like cosine of A, if we take that inverse of that trig function, we are popping out this angle measure right here, this A, and we are finding that angle measure. So we have to apply this M angle because we are trying to find the degree of the angle. So you have to apply this M angle to our letter. You have to do this. And we use these inverse functions to find missing acute angles on our right triangle. So missing angle, use inverse trig. I even write it down because you need to know. Missing angles, inverse trig. You gotta use inverse trig to find these missing angles. To do some practice, we have example 1, and this is more just plugging into our calculator, figuring out what's what. So doing the inverse tangent of 3.2. Hold on, let's write it out. I'm getting ahead of myself. So when actually like working with this and how it works, you're doing inverse tangent of 3.2. You're canceling out the tangent with the inverse. You're ending up with this on the inside because it's multiplying. But we'd get 72.6 and rounded to the nearest tenth. That's all I want. So, I'll flesh it out more when we do the cosine one. So let's do the inverse sine of 0.55. That's 33.36. I'm going to round up to 4. And then I'll rate this one out. Cosine of C is equal to 0.85 or 87. So we are starting with this cosine of C is equal to 0.87. What this inverse is doing, and I'm going to illustrate it out, we are multiplying to get rid of this cosine with the inverse. So adding that cosine of -1 to this side is going to cancel out this cosine right here. When I multiply on one side by one thing, I have to add it to the other. So I have to add this cosine of -1 to the right side. So now I'm going to cover up this because we kind of have a lot going on. I have this cosine of -1 times cosine of C is equal to 0.87 times the cosine inverse. These two cosines are now going to cancel out. Kind of think of it as like letter by letter canceling each other out. If that makes you happy. So these cosines are canceled out, which since now these trig functions are canceled out, this c now has to get an angle measure added onto it. So we are finding the angle measure of c. That's now equal to our cosine inverse times our 0.87. So when I write it out, it ended up looking like this. And this right here is what I plug into my calculator. Ow, I just stabbed myself like really hard with the pen. Now, you might be wondering, oh, how did these parentheses just pop into play? I mean, it would be the same thing if you just wrote cosine inverse 0.87. But the parentheses are nice. It's given to you on your calculator. And also, when we start multiplying a lot of things together, parentheses make it nice. So when I type in cosine of -1, cosine, inverse cosine of 0.87, I'm going to get the angle measure of 29.5. There we go. That's applying all of our cosine stuff, all of our inverse trig stuff. We can use this inverse trig. Oh, crap. I do need it. Oh, my notebook better be in here. I forgot that I didn't draw in the triangles. Okay, my notebook is in my bag. I forgot that I didn't draw the triangles for these notes. Oh, shoot. I got so much crap just flying everywhere. Alright. There we go. Well, that means I can actually write this out. Alright. With inverse trig, we can start using that to help us solve right triangles, the main purpose of this lesson. Now, what does it mean to solve a right triangle? Well, that means to find all unknowns. All unknown, not unknowns. Unknown side lengths and angle measures. Now, we can solve a right triangle when we know either of the following. If we know two side lengths, then we can find a right triangle. And if we know one side length and the measure of one acute angle, then we can find the missing information on a triangle. We have two examples to go through. And my page is blank because I did not do it or did not write it out. All right. So, example 1. Let's say we have triangle ABC. This is a right triangle, and I am given the measurements 24 and 25. The first thing I am going to do, find all unknowns. What do I mean by find all unknowns? I mean I'm going to label all my unknowns. I'm going to pick out what is the things I need to find. That being the measurement of angle C, the measurement of angle A, and the measurement, well, the length of C, the small side length. This is C. This would be A. This would be B. Given like how the triangle is working. So I need to find the measurement of angle C, the measurement of angle A, and the small side length of C. Now, we can go at this one of two ways. Actually, there's not really one of two ways. We kind of got to start in one position. When we are given a triangle with two side lengths, the first thing we should do when we are given a triangle with two side lengths is step 2. Find the remaining side length. In this case, C. So, I want to find C. How am I going to do that? Well, we can use the Pythagorean theorem. So, given that 25 is my hypotenuse, because it is opposite of that right angle, I can write out 25 squared is equal to 24 squared plus C squared. And now I can solve for C. So 25 squared is 625, which is equal to 576 plus C squared. Subtracting that 576 over to the other side, I'd end up with 49 is equal to C squared. Doing the inverse of that square, I'm going to end up with a C of 7. So that is one of my answers done. C is equal to 7. Now that we know C is 7, it'll make it easier to find angle measures. Why do I say it's easier to find angle measures? Well, now I can use any of the trig ratios I want in order to find out A and C. So our third step will be to find an angle measure. In our case, let's say angle A. I want to find the measurement of angle A first. So given angle A, let's say I want to do let's do tangent. We haven't done tangent today. That means I need to find the opposite angle from A, which would be 24. So I can label this as opposite. And since I already have the hypotenuse labeled, which this carries over from doing Pythagorean theorem, because 25 will always be the hypotenuse because it is opposite of that right angle. That means the 7 would be adjacent to angle A. So that means when I do tangent, which would be opposite over adjacent, I will have the tangent of A is equal to 24 over 7. And since I'm trying to find an angle measure, that means I need to do the inverse of tangent. So multiply this tangent of A by the inverse tangent. And since I did it to one side, I need to do it to the other. So I need to multiply inverse tangent to the other side. So that means I will have the measurement of angle A, which is equal to the inverse tangent of 24 over 7. And that's going to get me the value of 24 over, nope, not caret. 24 over 7 gives me 73.7. So that's my angle measure for A, 73.7. And now step 4, find remaining value. In our case, is the measurement at angle C. Now, you can do this one of two ways. You can either do a trig function in order to find angle C, and that would be perfectly okay. But since I already know two of these angle measures, I could just do 180 minus 90 minus 73.7 and get out whatever C is. And in this case, angle C would be 16.3. And those are the 3 measurements I needed to find. Not too bad at all. We'll do another problem. I should have enough room for this. And I'm not going to do all this labeling. We can follow the rules. Step 3, it could be find an angle measure or missing side length. It depends on what you have given to you. This is not the definitive order, but it should be something you're looking out for when it comes to these problems. Last example for day 1, and then we'll get into day 2. And day 2 is a little talky, so we'll hopefully get it done. So this is going to be the triangle YZX. It's a right triangle. We're given, what are we given? 18.4. I'm given 41. And I want to find out everything else. So we're going to list off what we need to find. So I'm going to write finding list. I need to find out the measurement of angle Y, this right here. I need to find out the length of mini y, right here. And I need to find out the length of mini x, right there. Those are my 3 values I'm trying to find. The first one that we should do, which might be the easiest one, is to find out what this measurement of angle y is. Since I'm already given a 41 in the right angle, I could add up everything that I have. Or I could subtract everything. So 180 minus 90 minus 41 is going to give me 49. So that's my measurement of angle y. 49. And I can write this in. I'll fill it in. Next, I should find one of my measurements. Let's do x. I think x will be my choice. So I can do this of one of 2 ways. I can either use the angle of 49 or the angle of 41. Either way I do it, I'll get the right answer, and depending on the trig setup, I will still get the right answer. Let's choose angle 41, though, for the one I'm using. So, since I'm working with 41, I need to find out its relationship with x. And it seems like I have to cross the whole triangle to even get to x. So that means this is going to be opposite from my angle of 41. This 18.4 is my only known value on this triangle, which is also opposite of the right angle, so it's going to be my hypotenuse. So that means when working with x, I'm going to be using sine because I am using opposite and hypotenuse. So I'll have sine is equal to opposite over hypotenuse. And then I can start plugging in what I know. With that, sine of 41 is equal to x over 18.4. And I can get that 18.4 to the other side to get x all by itself. Note that since this is the lesson we learned about inverses, we do not need to take the inverse of everything. We can just do sine of 41. We don't have to do inverse sine of 41. You're not going to get the right answer if you do the inverse of sine of 41. So you need to keep in mind that the inverse trig functions only work for finding angle measures, not for finding side lengths. I can even demonstrate this after I get the right answer. So 18.4 times sine of 41 is going to give me 12.07. So x will equal 12.1 because I'm going to round up. That's my x. And to demonstrate the wrong answer, I will plug in 18.4, do the inverse of 41. I get a domain error. That ain't right. You gotta use the right trig function. That means y is our last one. Since I already have labeling for x and the hypotenuse, I'm going to just label the y as adjacent and use 41. So that means, also, I'm going to say this right now. When we are finding missing values, like since I found this x, I would recommend not using what you have found in your other solutions, which is why I am not using like this measurement of 49 in like finding all of these solutions. I'm trying to find out everything with what I was given already. Like I was given this 41 at the start, so I'm going to use the angle 41 for everything. I know 49 is a clean number, but I'd rather not use it just in case if it was wrong. So I would recommend always using only the given information to find out what these are. Do not use like 12.1 to find out what y is. You could do tangent, but I would probably mark it wrong because of the rounding. So I would just stick with using what is given. Now in the case of up here, just be careful. Again, just be careful. I guess it's a different case scenario since you're using the side lengths to find angle measures. So it's a different case. But be careful with the information that you are using. Anyways, I'm going to use 41 still. And since y is adjacent to the angle 41, and since I have the hypotenuse of 18.4, I'm using cosine. Cosine is adjacent over hypotenuse. So that means I will be doing the cosine of 41. That is equal to y over 18.4. To get rid of 18.4, I get to multiply it to the other side. And that means my y value will end up being, we'll see, 18.4 times cosine of 41 gives me 13.9. Rounding up. And those are my values that I have found. All right. That is inverse trig. We do have application problems that go with it, which kind of revolves into day 2, or evolves into day 2. Now, after this, okay, I'm just going to explain this. So, we are given a triangle, and we have to use inverse trig to work with it. I'm giving you a story problem. It's based off of the Charlie and the Chocolate Factory play that Fenton High School put on a couple weeks ago. And because of that play, Fenton decided to make improvements to their auditorium. They plan on getting new seating arrangements and a new stage to accommodate those seats. This new stage will be a raked stage to help the audience enjoy the show better. What's a raked stage, you might be asking? It's a stage that has an elevation difference. So like one part will be taller than the other. This diagram down here shows it best. Like this would be the front of the stage, and this would be the back of the stage. The contractors were told that the angle of elevation could be no more than 5 degrees, so that the props would not roll out the stage. This meant that they had free range to make the stage to their own likings as long as they don't go above the angle of elevation. Your task was to find the length of the stage and find a length of the stage and find a rise of the stage that followed the criteria of not having an angle of elevation more than 5 degrees. You did not work in groups in this. You will not be working in groups, so it doesn't matter. And then we will I'll explain what we pretty much did. So basically what we saw is that this length of stage in this rise of stage dealt with the sine function because we have our angle of elevation right here. This was our no more than 5-degree angle. So this rise of stage and the length of stage resembled the sine trig function. When we write out sine, we have the rise of stage over the length of stage. With this being the opposite side length and this being the hypotenuse. This is also a right angle. So using that in mind, we could do stuff with it. This was a lot of kind of plug and chug, choose your own adventure type of deal with the side lengths. Your goal was to find a ratio to plug into inverse sine in order to get an angle that was smaller. Let's just say, for example, I want this rise to be 50 and this length to be 80. So when I set this up, I would have sine of, let's call this angle, let's just say angle A. So this will be the sine of angle A, which is equal to 50 over 80, opposite over hypotenuse, multiplying by this inverse of sine. Because I'm trying to find out an angle measure, I have to take the inverse of this sine. I would end up now with sine inverse of 50 over 80. These sines cancel out. So now I'm trying to find the angle measure of A. And now I can plug in what you found, or what I'm working with right now. Which these are just two numbers that I pulled up. I said 50 for the rise, 80 for the length. Let's work with those measurements and see where I get with that angle. So let's do the inverse of 50 over 80 and see what we get. I got an angle of 38.68. This is very much bigger, almost 8 times bigger than what I want for my angle of elevation. So that means 50 and 80 do not work. So I need to find a different either rise or length to work with in order to get in this ratio range. What we've found when working with this is that the length of stage and the rise of stage were drastically different in their angle, in their measurements in general. I saw lengths of stages in the ranges of 35 through 60, which is decently big. Let's say we're working in feet. And I saw rises of stages going from 2 to 6. That's what I saw today. It's a significant ratio. It's a big difference from what we have for like 50 and 8. If we reduce this down, it'd be like a 5 and 8. Yeah, that's a very big fraction you're working with. The fractions that you're working with, like right here, very small. The increase is super duper small. Like you're in the ranges of like 3 to 4 with the angle of elevation right here. I think a lot of you guys got an angle of elevation around 4 to 4.9. This was the common range I saw with your angle of elevations. And this was kind of just a practice of what can you work with and just trying to problem solve. It's a good problem solving problem because you had to find the trig ratio to work with and then also realize, oh, I need to find the angle and I need to find values that will fit this criteria. It's a good problem solving question, and yeah, I think it was a really good one. And I had to make it, so of course I think it's good. But anyways, that's it for trig functions. Your test, when you're watching this, would be on Thursday. I believe that is the 20th of March. Yeah. Good luck.